Thanks for having me here, and I must first of all excuse myself because now on the bottom floor there is some refurbishment, and I don't know if that's going to cause disturbances on the sound, but let's see. They started drilling in the walls downstairs, so sorry for this. Let's hope the microphone keeps that sound quiet for us all. So I'm here to present the paper really that I was able to publish in the special issue on machine learning in tribology, edited by Max Marian and Stefan Tremmel this summer. And I will give you the theoretical backbone of this physics-informed neural network. My name is Andreas Almqvist, and after I bore you with this, I will let in Sagar Said from MathWorks to actually run a demo comparing my homebrew code with exact partial derivatives for the stochastic gradient descent method with a routine that is built directly within the deep learning toolbox in MATLAB. Yeah, and the routine that I have composed may be found here at the MATLAB File Central. If you Google MathWorks and my name, perhaps you find that File Central and you can download it. Actually, I think Sagar will help you with that also later on. But before we move into the world of physics-informed neural networks, let's lay the theoretical backbone by just having a simplistic 1D curve-fitting ANN. And for this, I mean, it suffices with having a very simplistic architecture, one hidden layer, k neurons, and a suitable choice of activation function. Could be tangents hyperbolicus or sigmoid. And from that, of course, with this simple architecture, we get the ANN output mathematically formulated as this sum with the weighted output from each node and then adding the last little output layer bias to it. So in order to train the network, we need a cost function to minimize. And typically we apply a quadratic cost function. And if we now have this simplistic expression for the ANN output, the approximation, we can also explicitly obtain the cost function as this double sum. Now, if we apply this simple ANN to solve a problem for a linear problem, then we will only need one single node in our hidden layer because with a linear activation function, we will perfectly resemble a linear expression, the best way possible to a data swarm if we want to make a linear regression of it. And as you see here, we can actually make the output weight a unity, and we don't need an output bias for this. With these settings, then the approximation is a linear function, of course, and the cost function is a very simplistic quadratic form. Now, training the network now consists of minimizing this cost function and doing that, we need to find the weights and the biases that does that. And with this explicit expression of the cost function, we can, of course, obtain those partial derivatives directly, as we see here on the bottom of the slide. I realize I may need a laser pointer at some point. Okay. So applying then the gradient descent method, that would mean that we are trying to to find these weights and biases, which minimize the cost function. And to do that, we iterate based on the partial derivatives of the cost function with respect to the bias and the weights. And to that, we also add this little feature called the learning rate, here denoted by lambda. And this, of course, means that if it converges, then we will have the weights and biases that minimize the cost function, and then the ANN is done. And training with the gradient descent for this simplistic case requires, of course, that you have some training data. And to do that, to create the training data, in this case, we just randomize a number of data points and then generate X and Y data. And then the training can easily be implemented in MATLAB by these the following lines of codes, and where you see that we have the explicit analytic expressions for the partial derivatives of the cost function with respect to the weights and biases. And then we can update them accordingly at the bottom line there. Now, what makes this specific one, this specific training algorithm, a stochastic one, is that we randomly pick these points. So therefore, it's called the stochastic gradient descent. And we can, or Sagar will later on show that we can choose this training function with the deep learning toolbox to obtain the same or very similar. So that's just the randomization. Okay, and we need both training and validation sets to check whether we have any reliable output. And to do this, in this simple case, we generate some data, some X and Y data, precisely this one. So we choose points X within 0, 1, and then generate a linear relationship 2x plus 3, and we add some noise to it, just to not have the exact straight line. Then we take half of those points, make them the training set, and we save the rest for validation. This training, it consists of epochs and batches. And during one epoch, we take the entire training data, but it's split into smaller batches. And then we use these to update the weights and biases. So each of these batches, they consist in turn of running this gradient descent method on a number of samples just before updating the weights and bias. And now with this, we can express the validation routine simply as that, simply as shown here to the bottom right. We only need to pass it the weights and the biases, the current weights and biases coming from the training batch, and then we compute the prediction, compare it to the real value, to our ground truth data, here called only Y, and then we have the validation performed. So running that training on this routine may look something like this. So we have in blue dots the training data and in red the validation. And we can see that it goes down, continues to come down, and we could, of course, or we could perhaps continue for a few more epochs without disturbing anything, but it's perhaps not worth it because we are at a quite accurate position at this moment after 20 epochs training. As you can see, if we compare this ANN output to the least square method, the output of the least square method. Sorry, jaha, sitter och presenterar. Yes. So now we are at the stage of giving the theory the backbone for the PINN. It's very simplistic, because if we now consider in 1D the Reynolds equation, it is very easy to understand how this implementation of the physics-informed neural network will be, because it's just accomplished by formulating the cost function so that it contains the physics of the problem, and that's done by presenting the Reynolds equation in operator form. And then perhaps you have to do some mathematical operations to carry that out in a appropriate way for writing the cost function or defining the cost function. So what remains to be done now from this point is, as we saw before, now we have the cost function. We need to find the gradients of the cost functions with respect to the weights and the biases, because this is the way, the means we have to minimize the cost function. We haven't said anything yet about the activation function, but since we know a little bit of the solution of the Reynolds equation, we know we have boundary, it's a boundary value problem, we have boundary conditions, and the solution I will present to you is with 0 boundary conditions. And then we know that, or we hope that we have some positive pressure in between so that we generate some lift to our bearing or whatever. And therefore we understand that we can easily represent the solution of the Reynolds equation just with a few nonlinear activation function modes. And I've chosen to use the sigmoid function, but you can use other functions, of course. And now again, having one single hidden layer, K neurons, we obtain the ANN output precisely as before, although phi is nonlinear, so it takes a little bit more effort to compute the analytic partial derivatives to the weights and the biases, but it's perfectly possible. And if you use the deep learning toolbox, you don't have to, because you can use its built-in auto differentiation. Plugging all that in the same type of system as before, we can use this neural network, which is then physics informed through the cost function, to solve the Reynolds equation. And this is what it might look like if you just play with the code that I provided you with. And I have given you here the initial data that I was using in order to obtain my first solution. But then when I had that, of course, I could use the weights and the biases to get much further and faster to a new solution. And those coefficients or those weights and biases are already in the code that Sagar will now show you. So from this, or soon, well, there's some small more things, some MATLAB details, and then I will let Sagar take over for the live demo. So the main loop, it will look like this now. We run an epoch, and in each epoch, we run the training algorithm for that batch. After this, we just redefine our weights from from the data passed to that training function, and we compute the cost function and the batch, and then the batch number, and then we continue the epochs. This, and inside the training loop, we have this stochastic gradient descent method, which then just picks a random integer between 1 and m is now the number of sort of nodes. You can call them grid nodes if you like, but you can choose them uniformly or non-uniformly, or however you like when you start. So it's not really a mesh dependent method, this one, which is a little bit interesting. And then you just pick your data point from that random number, from the input with that random number, and with that you can compute the operator functions, and of course then you can compute the prediction and all the partial derivatives, compare this to the cost function, and continue. Now, time for the MATLAB live demo. So I guess, Jara, you would have to help Sagar to become the presenter now.
Yeah, so
I stop share.
So if you stop the share, then Sagar should be able to
yes,
share and unmute.
Great, I was able to unmute myself. Can you see my screen?
Yes.
Do you see the right screen where I'm showing my browser?
Yes.
Okay, great. So hi everyone. Thanks Andreas for giving me the opportunity to co-present with you, and thanks to the organizers for allowing me to be here. So I thought, and me and Andreas, we both agreed that let's try to make it a bit interactive, this session, and interactive in the sense that when I show the code, maybe you could also try it out on your web browser. So accordingly, I have pasted a link in the chat. This is the same link which I'm showing right now in my browser. If you click on that, you will be taken to this interface, which is called MATLAB Drive, which is the cloud storage of MathWorks provided to anyone who has a MathWorks account. I suppose most of you would have a MathWorks account since your universities have access to the license. If you personally don't have a license or have not created an account, you could do it later on and just observe what I'm trying to do. But for those who are interested to follow along, just click on the website, sign in with your MathWorks account, and then on this you will see these two files. One of them is Andreas' version, which he just showed in the presentation, and the second one is made using the deep learning toolbox, and we'll be comparing both of them side by side to show the similarities and few of the differences, the pros and cons of both approaches. So if you're on this page, you go to add to my files and say copy folder, and it will create a copy of these two files in your MATLAB Drive. So if when I do this, I have already copied it, so I need to give it a new name. So let's say new, and I rename it. So then I have it here, and I could right click on it and say open in MATLAB Online. I had a previous session running, so, and then it will open up the file in the web browser on this web address called matlab.mathworks.com, which is basically the cloud version of MATLAB running on your browser. So yeah. Sometimes it can be a bit buggy. All right. Okay. Yeah. I would instead use the installed version for my demo's sake. As I said, sometimes it can be a bit clunky. You could very well try it in the browser, but for demonstration purpose, I will use my installed version, where I have Andreas's version on the left-hand side, which is the traditional M file, which we all know how to create in MATLAB. On the right-hand side, there is what we call as the .mlx file, which stands for MATLAB live script, which is code along with some interactive text, equations, output, everything in one document. So very similar, but provides you the possibility to add some description on what you're doing in the code. So to make comparison easy, I have placed some bookmarks at several strategic locations wherever the code seems to coincide. So for instance, here is where I'm clearing all my variables in the workspace, making things nice and tidy. And the same corresponding section Andreas code is on the left. And in live scripts, the way you run a section, so for instance, this is a section, you just press on this blue bar and the code is executed, right? So I will do this step by step. So first we cleared everything. Over here is what we call the input section. So here we define, for instance, the mesh. The problem is meshless, but we have decided to take 21 points in the domain where we will compare the, where we'll try to minimize the cost function basically for the neural network. Then some Reynolds equation dependent parameters, K, number of epochs, 600, mini batch size. Andreas described what these mean in his presentations, the learning rate, initial conditions, so on and so forth. So when I execute it, when I go back to a MATLAB, all these variables are now created in the workspace, right? And then this is the corresponding section which Andreas prepared. Things are quite similar if we follow along. This is the place where Andreas is initializing his weights and biases. And these are the quantities which we would like to refine in the training process and get to a converged solution, which will predict the right output, the solution of the Reynolds equation, right? So very similar here, we are randomly initializing the weights and biases. We club all these weights and biases in a variable called params. Then we mesh our domain. We divide the space from 0 to 1 in 21 points, and which is stored in this variable called x. Andreas has the same. Here is a small difference, and perhaps some of you might know, or some of you may not. MATLAB provides what is called as data store objects. So data store are special type of variables which make handling of big data easy. For instance, if you have a lot of data which cannot fit in your memory, then data store is the object to use. It also provides a bunch of nice functions like read the next, or arrange, or combine, and all other cool features if you're really dealing with big data without having to sacrifice your RAM or so on. So this is one piece of difference which I have used in my code. And then a little more nuanced version of the code where I have created a mini batch queue object, which Andreas doesn't have. The mini batch queue object basically says that, okay, MATLAB, create batches of my data of size, mini batch size, which is 1 in this case. And also it sets the execution environment. So I'm running my code, or I will be running my code on a 4-core CPU machine. But if I make the execution environment, if I have a GPU, I could even make it as a GPU. So just by changing this to a GPU, I can get speed up in my code by using the power of a GPU. And then we initialize the visualization. So in here, we are going to visualize how the loss reduces with the iteration. So, all right, let's go down a bit. Then we enter the section called train in the network. And as Andreas said, he has a for loop, which loops over several epochs. And this is the most important piece of line, which does the heavy lifting, basically. So it's the train neural network function, which Andreas has defined at the bottom. And when I say heavy lifting, I mean both computation as well as writing the function itself is quite time consuming, because Andreas has taken a lot of efforts to to define the operations in the layers, as well as the activation function, then calculating the derivatives, exact derivatives by hand coding. And you can imagine a scenario where calculating these values might become very tedious if you have multiple layers and multiple nodes and so on and so forth. So this is the function which does most of the heavy lifting. It's quite a long one, but yeah, really good effort in implementing this, Andreas. But if you compare that function, train neural network, in the MATLAB or the deep learning toolbox framework, this is these two lines basically. So the first one is to calculate the gradients. So this will call an ACC func, which is a function I have defined towards the end. So if we go to model gradients, so this is the function which calculates the gradients, and this is the command DL gradient, which is deep learning gradient, which will calculate the gradients we want. So the first derivative is calculated like this, and the second derivative is calculated like that. So we don't have to go through this manual derivative process. That's in my opinion the only big advantage of using the deep learning toolbox, that you get the framework to use these functions without having to bother yourself with manual coding, right? So those were some of the user-defined functions, and let's go back to our comparison one-on-one. Okay, here we go. So these two lines are basically done by this, and then we estimate the updated parameters by doing this stochastic gradient descent momentum update method, right? So this is the gradient update method, which or the parameter update method, which Andreas spoke. And finally, we just loop over this this piece of code, and at the end evaluate our model's prediction. So I'll first run Andreas's code. I see we have just 4 minutes remaining. Oops, I realize Zoom is a bit hides my figure. Okay. So this is how the loss function is reducing across iterations. And we have set the number of iterations to be 600. And this is basically the prediction. You can see it's not very good. This is the analytical solution, the blue line, and the dotted one is the prediction from the physics-inspired neural network. And that's because we have restricted ourselves to a very small number of epochs. And maybe that learning rate also is not very fine-tuned. So it's kind of an experiment. You start off with some parameters, and then you need to play with these values, maybe increase it to 10-fold or change this value to 42 or 80, 84, and so on and so forth. So this is an exercise. Again, you need to know what are your fine-tuned values. But then we are fortunate that Andreas has converged onto values which are very similar to the final answer. So this is basically what we want the network to learn, predict, right? These are the golden values, the weights and the biases. And if we use these values to make the prediction, then you can see that we are very close to the final answer. Hence the loss function is very small to start with, and it's reducing across epochs. And finally, at the end of the 600th epoch, we get the converged solution.
I mainly played with sorry to Bargin. I mainly played with the number of epochs and the learning rate, and then I, successively brought down the error and used for each time I used the output weights and biases as input for the next.
Right. That's one approach. The other one would be to play with the decay rate of the learning rate. So initially you would like to have a higher learning rate because you are too far away from your ideal output. But over time, when you converge to the final solution, you would like to reduce it so that it doesn't oscillate a lot. So that's other. And we can run the deep learning version, deep learning toolbox version. And it's running when you see that. And when you click on it, it will take you to the section which is executing. And you can see this is the loss function. I must confess the deep learning toolbox version is slower, much slower than Andreas' version. And the reason being that Andreas is hand coding these derivatives, whereas here, these derivatives are calculated using automatic differentiation in the background. So there is a significantly higher overhead to do it. But if you pay this cost, what you get is convenience, right? You can save a lot of time not having to bother with this. And the moment you introduce another layer, you don't have to create these series of operations again. You just write DL gradient again one more time, and you're good to go. If you have a GPU, this will be much faster. You don't have to change any line of the code. Just say execution environment GPU, and you can use a GPU. So basically, so yeah, that was basically what I wanted to show. If you get the opportunity, just play around with these two codes. It's about to finish now, the epochs. Once it goes 600, yeah. I can stop sharing my screen once it goes to 600, maybe just as a nice closing point. Okay, then you can see actually how it is progressed. And again, the prediction is bad, I think, because I have not used the fine-tuned weights. I have used random values. But if I use these, it will be nice. So I'll then stop sharing my screen. If you have any questions, I'll be happy to take them, or we'll be happy to take them.
Thank you very much, Sagar. And